Okay, to understand properties, there are some important points you need to remember, which I have listed down here. So what does the first point say? The first point says the ratio of two extensive properties is going to be an intensive property. Okay, now the example of this we have seen in the last diagram. So what we have taken in the last diagram, we have taken a room full of air. In the second diagram, we have divided that room into two equal parts with a rigid boundary, two equal compartments. Okay, now to understand this, if we take the density of the previous room without dividing that into two equal compartments, if we take the density, that density is going to be mass by volume, where mass is going to be the mass of air in that room and volume is going to be the volume of air in that room. Okay, now in the second case, what happens, we have divided that room into two equal parts. Now in each of the compartments, the mass is going to be m by 2 and volume is going to be v by 2, since the room is divided into two equal parts. Now what is going to be the new density in any of the compartment? Now in any of the compartment, suppose in this compartment, the density is going to be m by 2 divided by v by 2, because mass of air in that compartment is m by 2 and volume has become v by 2. Now if 2 gets cancelled, this will become rho equals to m by v. Okay, now if we see that the previous case, density in previous case and density in the second case is going to be exactly same, that means even if we divide the room into two equal parts, this density has not changed itself. That means density does not depend on mass. So this is going to be intensive property. Now to get this intensive property, we have taken the ratio of two extensive properties. Mass is an extensive property which depends on the size or mass. Volume is also an extensive property which depends on the mass or size. Okay, now if you take the ratio of these two, we are getting an intensive property. So this is the saying of the first point. Now what does the second point say? Specific properties are intensive. Now in specific, what happens, if we use the word specific, we already define a region. Now for example, if we take a specific property like specific enthalpy, what happens? It means enthalpy per unit mass. So if already the region is defined, that means you cannot increase or decrease it. Your mass is already constant. So by using the word specific, and another example is going to be specific weight. So this means weight per unit volume. By unit volume or by unit mass is going to be the case in case of specific. Okay, now by saying per unit mass or per unit volume, we already define a region. Now in that region, whatever the properties are going to be is going to be intensive, because if you define a region, that doesn't change the size of it. Okay, now in the third place, what happens? Properties are independent of past history. Obviously properties does not depend on the past history. Suppose there is a pan of water and you have boiled it to 100 degrees centigrade. It will never depend on whatever the temperature of it was before. Okay, it will always reach 100 degrees as boiling point. Okay, it doesn't mean that if the water before was at 0 degrees centigrade, so this temperature, now the boiling temperature will be something else. If the water body had a temperature of 5 degrees centigrade, now the boiling temperature is going to be something else. No, it's not like that. Whatever the temperature it has now, it does not depend on any of the properties which it had earlier. Okay, so temperature is also properties. So in this case, we can say that properties are independent of past history. Whatever the history of the property is, it is not going to affect the present property of the system. Now in the fourth point, what you see, properties are exact differentials. Now in the engineering mathematics, there was a saying, if this is the case of a differential equation mdx plus ndy, to have the exact differential, you need to say that dou n by dou x when y is constant must be equal to dou n by dou y when x is constant. Okay, now if we differentiate that n part with respect to x when taking y as constant, must be equal to, if we differentiate that m part with respect to y when x is constant. Okay, now this will give us the condition of exact differentials. Okay, now in a simple word, if you want to mean the properties are exact differential, mean if you go from stage 1 to stage 2, the difference is going to give you the exact difference of this. Whatever the change in volume, if volume is a property, whatever the change in volume, you can directly get the change in volume by differentiating. Whereas in case of heat and work, this will not be the case, because these are not properties. Heat and work are not properties. So for properties like volume, you will get the change in by directly differentiating them in case of exact differentials. So properties are exact differentials. Okay, the next thing is state of a system. What does the state of a system mean? State of a system means the condition of the system. Okay, now for example, if we take a system here, if you want to know the state of the system, you have to say what is the condition of the system, and these conditions are expressed, these conditions are defined by the properties in it. Suppose pressure, temperature, volume, mass, whatever the properties it is going to have, these are going to define the state of a system. Now if we want to say that the system is in state, if we say that this system is in state, we need to consider that each of these properties is going to have a fixed and definite value. Okay, if these things does not have any specific value, we cannot say that this is a state. Suppose the pressure is continuously changing or temperature is continuously changing of a system, then we cannot say that this system is going to be in a state. Okay, so I'm again telling that if we want to say that the system is in a state, we need to have each and every definite value of whatever the properties are going to be there. Whatever the properties are going to be there, each and every one of the property must have some fixed and definite value. Okay. Okay, the next thing would be Gibbs phase rule. Now what does a Gibbs phase rule tell us? Gibbs phase rule will give us the number of properties which we need to fix, so that each and every properties is going to be fixed in that region. For example, suppose there are m number of properties in a system. Okay, now out of that m number of properties like temperature, pressure, volume, density, whatever are these, m number of properties are there. Now out of these n are independent properties. Okay, n number of properties are independent properties. Independent properties means these properties are to themselves only. This does not depend any other properties to define themselves. Okay, so if we say that these are the total number of properties and these are the independent properties, then the number of dependent properties is going to be m minus n. Okay, out of all these properties, n is dependent, so m minus n are going to be independent properties. Now Gibbs phase rule will give us the value of n. Okay, give us the value of n, that is the number of properties. Now if we define these n properties very clearly, these m minus n properties which are dependent on these n properties, we will define them automatically. Will be defined automatically. Okay, so I'll say this again to make this understand. M is going to be the total number of properties, n is going to be independent properties, and m minus n are the remaining, whichever the properties are remaining are dependent properties. These number of properties are going to depend on this number of independent properties. For example, there are three properties in a system. Suppose in a system there are three properties: mass, volume, and density. Okay, density. So what are the total number of properties here? The total number of properties here are 3. That is, m is going to be 3. Now which of the properties are independent? Mass and volume is going to be independent. Okay, mass and volume does not depend on each other. So n, that is independent, is going to be 2. Now how many properties are going to be dependent? That will be m minus n, that is 3 minus 2. 3 minus 2 equals to 1. One of the properties is going to be density. Okay, these will depend on both these properties, that is mass by volume. Okay, so this is the thing, and the number of n is given by Gibbs phase rule by this formula. Okay, using this formula we can get the value of n, that is whatever number of independent properties are there. Now in this formula, what we have said that p plus f equals to c plus 2. Now what is p? P is going to act as a number of phases. Okay, how many number of phases are there? Solid, liquid, gas, how many number of phases are there? This will be defined by p. Okay, f is going to give us the n value, that is degree of freedom. Whatever the number of properties you need to fix, so that each and every properties is going to be defined, this n value will be given to us by the term f. C is going to be the number of components. Suppose water is a component, that doesn't mean that ice is another component and steam is another component. If H2 is making them, then ice, water and steam is going to be considered as same component. So like that, how many components are there in a system will be given as by C, and plus 2 is constant. We'll see one numerical in the next video. Okay, So let us see some examples of how to find the value of n, or how to find the degree of freedom. That means how to find the number of properties we need to fix so that all the properties are known. Okay, now we have taken three systems here. We will explain each and every system with this formula. From this formula we need to find f. F is going to coincide with the value of n. If we find f, that means it will tell us about the number of properties we need to fix. Okay, so the first system is going to be full of water, that is H2O. Okay, now in this total system, what are the number of components? Components means whatever there are. If this total thing is made up of only single molecule means one type of molecule, then this total thing will be considered as one component. Okay, so in here the total number of component is 1, that is liquid water. Number of phases, that means number of phases means what are the number of phases? Liquid, solid, liquid, gas, how many phases are there? So there is only liquid phase. Okay, so this phase number is going to be 1. Now if you put this value in this equation, what will you get? P value is 1 plus F is equals to C value is 1 plus 2. From here we will get F is equals to 2. That means if we fix only two properties, all the properties of the system are going to be known. Now in the second case, I have given two phases. One is steam and one is water. Okay, now steam is a phase of water. Steam is a phase of water. That doesn't mean steam is there, H2 is there, the component are going to be 2. No, component is same, but they are in different phases. Okay, so in here number of component is going to be 1 only, because this steam is also made up of H2O, this is water is also made up of H2O. So number of component is going to be 1, but they are in two different phases now. One is in gaseous phase and one is in liquid phase. So number of phases is going to be 2 here. If we put the value, we will get 2 plus F is equals to 1 plus 2. From here we will get F is equals to 1. So for this system, if we fix only one of the properties, we will find out all the properties of this system. Now in this case, we have taken a special case of ice, water and steam. All three are there. Okay, all three are there. Now from there, again ice is also a solid phase of the water, steam is also a gaseous phase of the water, and this liquid phase is water. Okay, so as all of these three phases are made up of only single type of molecule only, that is H2O, this total thing will be considered as one number of component. Okay, so component is going to be 1. Now how many phases are there? There are 3 phases. If we put here 3 plus F is equals to 1 plus 2. Now we get F is equals to 0. That means none of the properties we need to fix to get the properties of the system. Now this is a special type of system where all these things are going to be there. Ice is also going to be there, H2 is also going to be there, steam is also going to be there. Okay, this special case is known as triple point. Triple point means all the 3 phases are going to be there. Okay, now if you want to know the temperature of the triple point is going to be 0.01 degrees centigrade or 273.16 Kelvin. This is a special case where all the 3 phases are going to be there. Now pressure, in that case the pressure is going to be 0.6117 kilopascal. Okay, this is a special case. So there none of the properties you need to define. To know all the properties of the system. Okay. The next thing will be process and path. Now what is a process and what is a path? Process is nothing but change of a system from one state to another. This change is only called process. Suppose there is a system which is in state 1 at the beginning and it has come to state 2. Now whatever the path it may come through, this doesn't matter to define a process. Just the change from state 1 to state 2 is going to be called as a process. Now what is a path? Now suppose from changing a state from state 1 to state 2, it has come across a number of equilibrium points. Okay, it has come across a number of equilibrium points. That now the path of that a series of equilibrium points is going to give us the path of the system. Okay, so what I am saying is before reaching from state 1 to state 2, there are number of equilibrium points through which the system passes through. If we connect this series of equilibrium states of that system, then this connection will give us the path. Now it may come through this one, it may come through this one. Now we will just need to define that those equilibrium points through which the system has passed through to come to this state. Okay, so this is called the path, and just the change is known as, change of the state is known as the process. Now in here, process is again divided into two equal parts. One is reversible and one is irreversible. Now what is reversible process? Reversible process is nothing but if we say that if a system is changed from state 1 to state 2 and the system has the ability to again go back from state 2 to state 1 in the same path without leaving any effect on the surrounding which it had before converting from state 1 to state 2, then this is called a reversible process. That means if a system had, there is a certain surrounding for this system in state 1, it has gone from state 1 to state 2, while reversing it should not leave any effect on the surrounding. That means the surrounding should not know that this thing has happened in the reverse way. Okay, so if there is no effect on the surrounding, then this path, that reverse path is going to be called as reversible. It is simply goes back to the same path, that doesn't mean it is reversible. It should not leave any effect. That is an important point. There are 2 points to be remembered. One is it should follow the exact path, and another thing, it should not leave any effect on the surrounding. These 2 points will meet to define a reversible process. Now what is irreversible process? Irreversible process is if a system is going from state 1 to state 2, if it is unable to go back to state 2 with the same path or leaving any effect on the surrounding, that this is going to be called as irreversible process. For example, from this diagram, suppose there is an inclined plane and a mass of block M, suppose a mass of block M is sliding through it. Okay, now it has come down here. Now if we push back it to this, the initial point, this doesn't mean that this is reversible process. Why? Because while coming down from here to here, there is some of the energies which is being expended due to friction. Okay, now if I am again pushing it back to this place, again some frictional energy, again some energy is expended due to friction only. Now in both these cases, while coming down from this state to this state, there is some energy expansion, and from again if I'm pushing this thing from again this place to initial place, again some energy is going to expand in terms of friction due to some frictional losses. Okay, so this thing cannot be reversible, so this will be called as irreversible. So for this we need to remember that friction is going to be the sole reason of irreversibility. If a system is irreversible, that means there is some friction. Okay, friction is the sole reason of irreversibility.